All right. So we got a velocity time graph. We've seen velocity time graphs kind of like this before, where we start off at an initial velocity that isn't zero, and if we're reading this like a story, it's getting faster and faster and faster as time goes by, right? Remember, this is a velocity time graph, not a position time graph. So velocity time graphs, we'll even label the axes. We can say that it's velocity, velocity, and we could throw in units of meters per second, and we could declare that the positive direction is east. Those are all reasonable things to do. Velocity in meters per second towards the east is the positive direction. But then along the horizontal axis, we might end up having time in seconds. And so none of that's really new. Other things that aren't new is we could talk about the meaning of slope. Well, on a velocity time graph, the slope, you guys shout it out. What's the slope on a velocity time graph mean?
Acceleration.
Acceleration. We just did a lab about that. So this is something that should be fresh in our minds. We say acceleration is equal to delta V over delta T. We also said previously in other lessons that the area under a velocity time graph is the displacement. So displacement. And once upon a time, we also said that sometimes we even think about the average velocity, V average, which I said usually I'll write it as VAVG for average for short, could be thought of as V1 plus V2 divided by 2, just sort of like a mean calculation way of talking about it, you know? And notice I got a V1 plus V2 divided by 2, and I happen to have a V1 and a V2 over here, so maybe this is something that's going to come up as being useful at some point today, right? All right, so these are three what I would call math facts that we've kind of got under our belts. And the first thing we want to do is derive the simplest equation of motion. And we have 5 equations of motion we're going to look at. Sometimes you see in YouTube videos, people will call them the big 5 or something like that, try to be dramatic. But really, these are 5 motion equations. We call these the kinematics equations of motion, and we use them to analyze how things move around. Now, really and truly, all this stuff is based on some calculus knowledge, but we're going to sort of sidestep the calculus side of things and make it simplified, okay? So this is a simplification to sort of skirt around calculus. For equation 1, we're going to start off by using the equation acceleration equals V2 minus V1 over delta t, and you'll notice that I'm going to drop the arrows over top of the things that I know are variables only just because it's less cumbersome when I write, not because I don't know any better, and I know that you guys know better too. So the arrows will be missing, okay? And we know that velocities should have arrows, accelerations should have arrows, displacement should have arrows, but it's hard to keep up with all the arrows, okay? So that's all we're dropping here. But what I want to do is, and we had to do some mastery of isolating, I just want to isolate V2. So if I had to isolate V2, I could take a look at this expression. I would first write out the expression acceleration equals V2 minus V1 over delta t. And in terms of how I'm going to get V2 all by itself, some of our math teachers in the building say clear the denominator. And so that's what I'm going to do first, delta t. Now there are other people, you may have had like a grade 7 or 8 teacher that says take the delta t over to the other side. I think that the weakness in that is like, how do you do it? How do you get the delta t over to the other side? Clearing the denominator, thinking about the operation by which I'm getting it to the other side is important, okay? In this case, to clear the denominator, I've got to multiply both sides by delta t. So the reason I bring that up is because when I was looking at mastery quizzes, some people were randomly subtracting delta t from both sides. There's nothing random about it. It's very systematic, right? We're clearing that denominator, we're getting it over. Anyway, then I could say, okay, and I said this once before, that usually stylistically people put time at the end of an expression, and I'm going to continue that tradition. V2 minus V1 is what's left behind on the right-hand side. And then again, we have some of our grade 7 and 8 teachers have taught us, take the V1 over to the other side. Again, not the strongest language. My own grade 7 and 8 teachers said it that way. What are we going to do? Well, we're going to use an operation to get rid of that V1. We're going to add V1 to both sides. So negative V1 plus positive V1, that's going to eliminate. And this is a little bit ugly because I haven't left myself enough space, but it would be A times delta t and then minus V1. So I think I'm going to write it out a little bit nicer. What I've really got is A times delta t minus V1 equals V2. Oh, sure. I'm sorry. You guys called me on it. Plus V1. Thank you. Here I am thinking about what's happening next on the page, and I made a silly mistake. All right. So now we'd say V2 is equal to V1, because remember, stylistically, people like to put the T at the end, V1 plus A delta T. And as simple as it seems, this is actually pretty much the same equation we started out with. We just isolated for the V2, and people will call that equation 1. Why do people even bother? Honestly, it's easier to type. Look, there's no denominators or anything like that, right? Sometimes it's a silly reason like that. It's isolated for a thing that we often want to know, the final velocity of something, and it's easy to type, okay? Equation 2, though. Equation 2 is maybe a little bit trickier. Equation 2, I want to find the displacement, and specifically I want to find the displacement for this graph. And so what I'm really doing, and I'm going to be a little bit Mickey Mouse about this, is I'm finding the area of a rectangle and an area of a triangle. And in a homework activity in the past, you guys had to do something like this, where we had to find the area of a rectangle and a triangle underneath of a graph. So here, I could take this graph and break it up into a rectangular area and a triangular area. And the sum of those two areas would be the displacement for that velocity time graph, because we're working with this math fact that the area of a VT graph is displacement, right? So we're kind of like tying these things together. And so if I look at the area of the rectangle, and I want to be like a really algebra-driven person right now, I say, well, I know that the area of a rectangle is base times height. I know that the area of a triangle is 1/2 base times height. Sometimes people say base times height divided by 2. Same thing, okay? But when I take this, I think I learned this stuff, and I want to say like grade 5, grade 6. I don't know. Like I can actually remember the teacher that taught it to me. She's retired now, Miss Heaver. But she taught me this stuff. I want to not leave it in that elementary school mode. I want to switch it over to useful variables that apply to this graph. So when I say base times height, look, this rectangle has a height of V1. Doesn't it have a base of delta T? Look at the dimensions that are on there, right? So I want to do this. I'm going to say, well, base times height really is V1 times delta T. Notice stylistically, again, I'm leaving the time last. I keep on harping on that one. Plus 1/2 times, and it looks to me like I've got base times height times 1/2. Okay, so the base would be delta T. The height, be careful, from here to here, this is the height. And that height is actually V2 minus V1. So the height is going to be V2 minus V1. And then I'm going to use my math language. I'm going to use distributive property. And when I say I want to use distributive property, what I mean is that 1/2 delta T, that, I'll just underline it, is going to multiply through the binomial. So even though I know that it's like a 2-term coefficient, 1/2 times delta T is a coefficient. It's a number. It's in disguise because I haven't subbed any values in yet, but I've got to multiply that coefficient through the binomial. Okay, so in my next level of simplification, I say, all right, well, V1 delta T plus 1/2. You remember I said I like to put the delta T's last. I know it would be 1/2 delta T times V2, but nobody writes it like that. They say 1/2 V2 times delta T, because the sequence doesn't matter when you're multiplying things like that. So 1/2 V2 delta T minus 1/2 V1 delta T. And then again, the math hat comes back on me again, and I say, hey, look, that guy there has a V1 and a delta T in it. That guy right there has a V1 and a delta T in it. What's the C word that I would use at this point if I was in a math classroom? Not commutative. It starts with a C-O-L-L. Collect. Collect like terms, yeah? Make a little note. Collect like terms. In this case, like terms means all the terms that have V1 delta T in them. I could say, all right, cool. I could say V1 delta T minus 1/2 V1 delta t plus 1/2 V2 delta t. Well, V1 delta t is basically in disguise. Isn't that just one whole V1 delta t? So a whole V1 delta t minus a half V1 delta t, well, that's going to just give me a half V1 delta t. Right? Plus a half V2 delta t. And then I think to myself, well, wait a minute, both of these guys got a half in them. Both of them got a delta t in them. What am I going to do? One of my favorite F words. Factor, honey. I'm going to factor it. You thought I was going to say something different. Factor. Zoe? She was so worried. All right. I saw the worry on your face. Factor out both the 1/2 and the delta t. Both of them are going to get factored out. Now, people factor it out in a kooky kind of way. First, I'll write it the way that I think I would do it if I was in a math class. If I was in a math class, I would factor it out 1/2 delta t times V1 plus V2. That's how I would do it if I was teaching my math class. But the way people deal with this is they say, okay, well, yeah, we factored it out, but then we're going to do a funny little thing. Remember, I said that people tend to put the delta t stylistically at the end? So people write it as V1 plus V2. They put it in the binomial brackets. Then they throw a delta t at the end. And then that 1/2, they do another funny thing. Isn't something multiplied by a half the same thing as that same something divided by 2? Look at that. Got a 2 there. Now this is still delta d. It's the same displacement that's been sort of filtering down all the way from the top. But the reason that I might talk about this one, you know, I'll put a little box around this. I'll call this my equation 2, no problem. But the reason that I might write it like this is because, hey, look, up here, can you see that V1 plus V2 divided by 2? We already declared that to be V average, right? You see what I'm talking about? In fact, if I highlight this thing yellow right now, and I highlight this thing yellow right now, it becomes really obvious that I could just rewrite. I'll call it equation 5 just because I want to. But equation 5 could be written like this. Delta D equals V average. I'll just write it as VAVG times delta T. And really all I've done is taken this yellow thing, put it here to make a nice, cute little expression. Well, why would you want that? Well, sometimes you know the average velocity. Sometimes you know the initial velocity and the final velocity. It's a matter of what you're told. It's a matter of being able to put puzzle pieces together, okay? So sometimes it's okay to have things written in slightly different ways to accommodate for that. Remember, we're always telling stories. Physics is oftentimes about telling stories, interpreting stories, and then analyzing stories. And we see that with the graphs. We're going to see that with the word problem type stuff as well, okay? All right, so that's equation 2 and like 5. I kind of jumped ahead on things there. Now equation 3. Equation 3 starts out in a similar way. Same way as equation 2, I should say. I start out with my displacement. I say, okay, well, displacement is actually going to be, for the graph in the top left-hand corner of this page, the sum of the rectangle plus the sum of the triangle. And just a reminder, when I say the sum of the rectangle and the triangle, I mean that rectangle and that triangle. And so since it starts out the same way, we can actually steal some information from what we've said before. And the information I want to steal is that the area of that rectangle would have V1 times delta T as its base times height, because we already had those thoughts. And the area of the triangle would be written as 1/2 delta T times V2 minus V1, again, because we already had those thoughts. But I want to do like something different this time. At this stage of the game, I'm going to highlight again V2 minus V1, and I want to peek back just a little bit. What I want to do to peek back here is to say, hey, look, this expression that I had here, V2 equals V1 plus A delta T, which we called equation 1, I could do like a little bit of math gymnastics. And when I say a little bit, I mean like truly a little bit. See, that's like a quick little math backflip there. And I could say, hey, V2 equals V1 plus A delta T could be written as V2 minus V1 equals A times delta T. See what I did there? Took that V1 over to the other side by subtracting V1 from both sides, right? And if I highlight that yellow, V2 minus V1, and I make the little statement, sub in. This is cute, right? Like I can take some stuff that I did once before, change it ever so slightly, and in the next line of math, I end up getting V1 delta T plus 1/2, delta T times, not V2 minus V1, but something a little bit easier, not a binomial anymore, A times delta T, right? That's cute. Everybody likes it when a binomial becomes a monomial. By everybody, I mean me. And then we say delta D is equal to, okay, well, hey, that's V1 delta T plus, and let me think this out, plus 1/2, but T times A times T. What could I write that as? Yeah? Yeah, you're right. A times delta T squared. Thank you, Zainab. Yep. A times delta T squared. Beautiful. That's actually a lot tidier. And so I want to put a box around this one. And the cute thing about this one is that this thing that I'm going to call equation 3 started off in the same way as equation 2, but it took a little bit of a different turn, right? This one involves initial velocity. The previous one did involve initial velocity. This one involves acceleration. The previous one didn't. And again, if we're telling stories about physics, sometimes you're told certain information and not other information. In this case, we didn't know the acceleration directly. This time we did. And so this is like just another tool in the toolbox that we're building, right? Based on stuff that we might know. Now, I want to put a quick little, where did I put my ruler? I know I had a ruler around here. Can I borrow your ruler? I'm going to steal this just for a second. I'll give your ruler back. But I want to just put a little line here. Quick little line there. Put that back there. I don't know whose ruler that is. And I want to make sure that we address something before it becomes a bigger thing. Quadratic formula. Hey, you guys in grade 11, everybody remembers back to grade 10, you saw trigonometry for the first time, you saw quadratic formulas for the first time, and some people have some math trauma surrounding quadratic formulas. Hands in the air if you have some math trauma surrounding quadratic formulas. Quadratic math trauma. Like maybe like 5 or 6 people, and then there are other people that just won't admit it publicly. So that's fine. We're gonna try and address it, okay? But we also wanna like make sure that at this point, I got to acknowledge that it's still a thing, okay? So when I look at this equation, equation number 3, it's actually a quadratic in disguise. Not even a very good disguise. Because if I take this delta D and I subtract it from both sides, what I'll end up getting is 0 equals V1 delta T plus 1/2 A delta T squared minus delta D. And I got to massage this just a little bit. I'm going to resequence the addition of these terms. And what I would do is I'd say 1/2 A times delta T squared plus V1 delta T minus delta D. And some people are going to see this, and some people aren't. I'm going to use my highlighter. 1/2 A V1, and the whole thing, negative delta D. If I go along here, and notice, it's a delta T squared, a delta T, and no T on this one, right? And if I remember back to the good old days of quadratics, I know that it was AX squared plus BX plus C. And if I label this and say, I know it's A for acceleration, but 1/2 A for acceleration is actually the A coefficient from the quadratic formula. V1 is the B coefficient from the quadratic formula. And the whole thing, whatever negative of delta D is, including the negative sign, is the c coefficient from the quadratic formula. And again, back in the good old days of quadratics, we would have said x equals negative b plus or minus the square root of b squared minus 4ac all over 2a, right? And we get to still say the same thing, only this time it's time. Delta t is equal to negative b, where b is actually v1, plus or minus the square root of b squared minus 4ac all over 2a. The only thing we need to recognize is that the a, b, and c are respectively 1/2 a, v1, and the negative of the delta d. Okay? Now, I don't want to do a question that solves this or deals with it right now. I just want to present it to you because it's another math tool in your toolbox that you already know, right? So like, if you know something already, why not like remember that you know it? That's all I'm saying with this, okay? So it's not a new equation. I'm not calling it equation 4 or anything like that. It's just relating equation 3 back to some math that we already know. Now equation 4. Equation 4, I want to start with equation 1. Start with equation 1. And what we said back in the day with equation 1 was that V2 equals V1 plus A times delta T. I want to do a little bit of math gymnastics. I don't want to show all my steps. If you want to go back and prove that I'm right or challenge if I'm wrong, you totally can. But what I want to claim is that if I do a little bit of math working here, I can re-isolate to get delta T all by itself. And delta T equals V2 minus V1 over A. I won't tell you why that's useful yet. But there'll be like mathematical, okay? It'll be sleight of hand. I like that, mathematical. So then, use equation 2. And equation 2, we said delta D equals the binomial V2 plus V1. Look, it's written right above, still highlighted yellow, V2 plus V1 divided by 2 times delta T. Now, I've already used yellow, so I'm going to use pink now. If I sub in to this delta T spot, the expression V2 minus V1 over A, that's going to be mathematically helpful for me, okay? So I'll tell you why it's going to be helpful. Let's write this thing out and see what happens. Delta D, I'll make a little comment. Sub in. Okay? Delta D equals V2 plus V1 over 2. Put brackets around it. Instead of delta T, I'm going to write V2 minus V1 over A. And as I look at this, I'm like, oh man, 2 binomials and their fractions? By golly. Shucks. Shucks is a good stand-in for how I feel right now. But when I have V2 minus V1 times V2 plus V1, there's another F word that comes to mind. What's the F word? 2 binomials. FOIL. FOIL. Look at this. V2 times V2, V1 times V1. Oops. That's my alarm reminding me that I have library duty at lunch. All right. So when I multiply through this and I do the foiling, and you can FOIL this out for yourself, if I have V2 plus V1 times V2 minus V1, do you remember the special FOIL that is? Yeah. It is. It's a difference of squares. And we end up getting V2 squared minus V1 squared divide across the numerator, and across the denominator I get just 2a. You're like, wait a minute, that's simplified out in an awful hurry. If I clear the fraction, multiply both sides by 2a, then I end up getting 2a delta D equals V2 squared minus V1 squared. Now for this particular equation, people often like to add the V1 squared to both sides just to isolate for one variable, because people always love to see one variable all by itself. Again, it's just style. But we end up getting V2 squared equals V1 squared plus 2a times delta D. And we call this one equation 4. And this kind of rounds out the big five, the 5 equations of motion that we're going to use to solve, frankly, a ton of problems in 1 dimension and 2 dimensions.